All right, we're doing 1526. All right, so this problem, first I'm going to draw the picture of what it is. So you have, now you see that these are labeled, there's different angles, and even though there's one mass, because they're at an angle and the angle's different, the tension is not the same. So this one is T2, this is T1, this is 37 degrees, and this is 53 degrees. Okay, now this is a static equilibrium problem. Static equilibrium is extremely important because that means that all the forces, when I sum forces, they're equal to 0. Okay, so normally, first of all, this is the mass. You have to look carefully. Some of them they're going to give you mass, some they're going to give you weight. So here I know the weight is mg because when we end up doing our free body diagram, a free body diagram shows all the forces that are acting on an object. So this is going to be 20 kilograms times 9.8 meters per second squared. So here I know the weight is 196 kilograms. Newtons, thank you. So the first thing they're going to do is they're going to ask you, draw your free body diagram. So your free body diagram shows all the forces acting in the direction in which they act. You don't put components in a free body diagram. So just doing this, T2, T1, and the weight, that's my free body diagram. In order to solve this problem, I want all my forces to go according to my sign convention. So my sign convention is going to be up and to the right is positive. So that means I want all my forces to go this way or this way. I don't like to do little shortcuts. I don't like to draw stuff in my picture. What I like to do is I like to do stuff to the side. So I'm going to take each of my tensions individually. This is T2. And I know that this is 53 degrees. Now, why did I draw it like this? Remember, this and this are alternate interior angles. So I'm just used to going like this. Here's my horizontal component, which would be T1x, which is going to be T1 cosine of 53 degrees. This is T2, sorry. And then from the head of this vector, I do the tail of the other. Remember, components are perpendicular to one another. So this is going to be T2y, which is T2 sine of 53. Okay? So this is my horizontal and vertical components. For the other one, here's T1. This angle here is 37 degrees. This is where I start. So T1x is equal to T1 cosine of 37. Why is it cosine? Because it's adjacent to the given angle. From the head of this vector, I'm going to do the tail of the other. So this would be T1y, which would be equal to T1 sine of 37 degrees. This is the most important part. Before I start summing forces, the directions of these arrows, head to tail, my components, are important. So first of all, I'm not just drawing a triangle. I'm drawing the components, which are vectors, and I need to be very careful the direction. All right, so now what I'm going to do is I'm going to redraw this and show all the components. So I have FG, and instead of T1 and T2, I'm going to replace it. So this one is T2 cosine of 53. This is T1 cosine of 37, and this is important. You see how these are going in opposite directions, and that's important. All right, so then this is going to be T2 sine of 53, and then up here I'm going to do T1 sine of 37. Now I'm home free. This is the point now where I'm going to be summing my forces. Where do I start? It doesn't really matter. So let's say I just start horizontally. Because this is in static equilibrium, so what I'm going to do first is I'm always going to write my sign convention. So I'm calling to the right positive. And now I'm saying summation of f of x is equal to ma. On an FRQ, you have to write this. If you don't write this, you don't get the point. Then you have to write is equal to 0. Now back in the day, they always taught, like when I was in college, you go up and to the right is 0 because the acceleration is 0 because it's in static equilibrium. I still do that, okay? Now on the AP test, they still want you to write is equal to 0. So now I'm going to look at my diagram and I'm going to say what forces are going in the x direction. So T2 cosine 53 is going to the right, so that's positive. So T2 cosine of 53 degrees. This one is going to the left, so that's negative T1 cosine of 37 degrees is equal to 0. Now, so that means T2 cosine of 53 is equal to T1 cosine of 37. I'm going to substitute one in terms of the other. It doesn't matter. My problem is I have one equation and I have two unknowns. All right? So then I'll say T2 cosine of 53 degrees divided by the cosine of 37 degrees is equal to T1. I'll now do this on my calculator. I'll do cosine of 53 divided by cosine of 37. So that comes out to be 0.75. T2 is equal to T1. Now you see I have one variable in terms of the other. So what I'm going to do now is, I'm going to sum forces in the y direction. There's my sign convention. Summation of, I'm calling up positive. Summation of f of y is equal to ma. This is equal to 0 because this is in static equilibrium. Now I'm looking at this picture. So T2 sine of 53, is that up or down? It's up, so it's positive. So I have T2 sine of 53 plus T1 sine of 37 minus f of g. Why is this negative? Because it's going down, is equal to 0. So now I'm going to have T2 sine of 53 plus, now what I'm going to do is I'm going to take this and substitute it in here for T1. Because now I want to eliminate a variable. So T2 sine of 53 plus, so instead of T1, I'm going to write 0.75 T2 sine of 37 is equal to 196. I took the f of g and I moved it on the other side and I put in the value. Now I'm going to collect all my like terms. So T2 times 0.8 plus 0.45 T2 is 196. So 1.25 T2 is equal to 196. So T2 is equal to, comes out to be 156.8, so we'll call that T2 is equal to 157 newtons. How do I find T1? Put it back in here. So T1 is 0.75 T2, so it's 0.75 times 157, so 117.75. So T1 is equal to 118 newtons. Step by step.